Periodic table. It's probably the most famous table in chemistry for sure, the periodic table. I've already pulled it up a couple times. Again, here is the periodic table laid out. Lots of different versions of it out there, different ones in their textbook that you'll see. Where did it come from? Well, as the elements, the pure elements were slowly being discovered, people started understanding that compounds were different elements put together, right, in a whole number of ratios, all that. They tried to understand how they were similar, these elements, and how they were different, that sort of thing. And people would arrange them maybe in terms of increasing size, increasing mass. They would arrange them by, well, these are all solids, where here's a gas, and here's a liquid. Maybe they would arrange them by, hey, these conduct electricity and these don't. Trying to figure out the connectivity between them, right? The similarities. 1869, Dmitri Mendeleev came along and arranged them in the way that we now see the periodic table. He organized them not by physical similarities, but by chemical. All right. So, for example, water is H2O. He said two hydrogens bind with one oxygen. He said, is there anything else that also kind of behaves that way? And sure enough, two hydrogens could also bind to one sulfur. So he said, okay, oxygen and sulfur chemically behave similar. I'm going to group them together. Okay. Another example, sodium chloride, table salt. There's one sodium and one chloride. All right. What else behaves that way? Well, actually, potassium does. Potassium combines in a 1-to-1 ratio with chlorine. So, okay, let's group sodium and potassium together. All right, you get the idea. So he grouped them like that. And after he grouped them together, he arranged them as far as increase in size, increase in mass, just small to big. Makes sense. And here's kind of a picture, an early representation of what Mendeleev did. All right. I already mentioned this. Like, here's sodium, which is Na. He put them in the same group as potassium. Potassium is a K. That's for the Latin kalium. All right. What else is in here? Rubidium, cesium is in here, lithium is in here. All right. Here's the one over. Where's the one with sulfur? Here it is. Oxygen he put in with sulfur. Same idea here. And so these he put together. It's not a perfect arrangement, but he was really onto something. He was absolutely correct and very insightful. Perhaps one of the biggest things that came from his rearrangement is he found holes. He found spots where increasing weight and yet grouped chemically together, there should be an element here, he thought, There's like these missing holes, and yet they didn't know of anything that would fit there. Of course, one way to interpret that, I guess, would be, well, I got it wrong. Right? This isn't a good way to group it together, that kind of idea. But he was confident enough about his arrangements where he actually predicted that there were additional elements out there that just no one had discovered yet. When you think about it, that's fairly bold, right? But he was that confident in his data and his understanding of it where he made that prediction, and sure enough, he was absolutely true. So, for example, right here in this group here with boron and aluminum, he predicted there should be these two things. Turns out he was absolutely right. He didn't have anything but one that weighs about 44. Here he predicted one that weighs about 68. Sure enough, turns out scandium and gallium. Here, one that weighs about 72 in this group. Group 4 is what he called it, along with carbon, actually. Sure, germanium, actually. And we found those later. Here's one over here. The missing element turned out to be technetium, the first artificial element, which we'll have to talk about. So he was absolutely right. And the periodic table now is grouped by chemical similarity. If you look at a full-blown periodic table, it would look something like this. Where, again, here's my first group, and let me see if I can zoom in a little bit on this. Go over here. Here's my first group. We've got hydrogen, lithium, sodium, potassium. They're all grouped the same way, so in that column. Next one, beryllium, magnesium, calcium, strontium, barium. Those are all, again, similar. Radium at the bottom there. Okay. We're going across here. We'll talk about why there's only 2 here in these groups and a bunch here. We'll look at all that in a second. But all of these will be grouped similarly. Over here, here's Fe, iron, along with ruthenium and osmium. Copper is along with silver and gold, interesting enough. Not too surprising that both silver and gold, these ones that we make coins out of, gee, they're in the same column. Yeah, they must chemically be similar. fact, the similarities, they don't react very well actually. But yeah, they're grouped together. Okay, carbon, silicon, germanium, tin, lead. That's kind of interesting that those are all in the same one. They do have similar chemistries, but not identical, and we'll have to delve into that a little bit. Fluorine, chlorine, bromine, iodine, acetone. Those are all grouped together, called the halogens. Very important class. And this extremely important one, this last column here, this last group of helium, neon, argon, krypton, xenon, radon, those are called the noble gases. Okay, and so grouped by chemical similarity. Right? Here is kind of how we see a modern periodic table right here, where it's not stretched way out. Stretched right out would be the most natural way to do it, but that makes a very long, thin periodic table. And truly speaking, this middle group right here are very rarely seen, very rarely used, and yet they take up all this space. Right? So what we do is actually just throw those two on the bottom here. That's these two. They're really stuck in right here, and you see here this is actually 57 through 71. So if you kind of split this off here and stretched it out and stuck this middle block in, you'd get that original arrangement. Okay, so this is how we usually see it. And again, here's our groups. Here's the one with sodium, potassium, right? That first group I talked about. Here's the one with the carbon and silicon, oxygen and sulfur, and those guys, right? So if you look up and down any one of these groups, you expect similar chemistries. Right? And because of that, these groups are given names because, well, they're grouped together. They kind of react similarly. They're actually given names, and you need to know these names. They're not that many, and they're pretty simple actually. So, for example, this first group here with lithium, hydrogen, lithium, and sodium, the alkali metals. The alkali. The second column, the alkaline metals. Okay, they're both metals for the most part, except hydrogen's not a metal. But otherwise, alkali and alkaline. So even the chemistries between that group 1 and group 2 are similar, but different enough chemically. They do react and make compounds slightly differently. If you go over here, this last group that I already mentioned are the noble gases with helium, neon, so know that. And the halogens, starting with fluorine and chlorine going down there. The halogens, important. These two names you're not really going to see a lot. Don't worry about remembering these two. The book does mention them. The chalcogens, and I don't even know how you say that. The pnictogens, I assume that P is probably silent. So the pnictogens, anyway. Don't worry about those two, but do know the halogens, do know the noble gases, do know the alkali and the alkaline. Okay, the ones at the bottom here, these last two, this row are the lanthanides, these are the actinides. You'll see those names, but again, in this class we're not really going to deal with those, so don't worry too much about those. Now, if you look at it, there's this middle section right here, this middle block. Right? Groups 3 through 12. Those are called the transition metals. They're going to have slightly different chemistries than the ones that are not in this transition metal block that I've circled in green. The green are the first 2 columns and these last 6 columns. Those are called the main group elements. Right? And the main group elements are the chemistries that are going to be easiest to understand what they do. The transition metals are a little different, a little more complicated, and we'll start to pick out those a little bit more. Okay, so main group elements, like I said, are boxed in green here. Another thing, if you look at the physical properties of these various elements, they've color coordinated it in this chart, which is nice. This tannish color down here, we can see our metals. Most of the elements on this table are metals. Right? These, they haven't produced them enough. These really big ones, they make them in labs. Some of them they haven't even fully named yet. That's why they have 3 letters on this table. So they produce them in labs. They're very unstable. They hang out for a couple microseconds and then they disintegrate. They're just too big to be stable. They're white here on this table, just not known yet, I guess. Okay, but look at that. Most of them are metals. Hydrogen, not really metal. Sometimes hydrogen is actually put over here right next to helium. It kind of has the chemistry in some cases like the other ones in group 1, or in some cases like the ones in group 17. Right? It is a non-metal, hydrogen, under normal pressure and temperature here. It's a gas, right? So in some ways it really does fit better right up here next to helium. But you'll see it in hydrogen too. I'd say it's a 50-50 sort of a thing. So hydrogen just doesn't know where you want to put it. And in fact, I thought I remembered seeing a chemical periodic table, that had that. Actually, I think it was this one that he kept coming up with. No, it wasn't that one either. No, we saw one where they did just that. They put hydrogen over here as well. All right, so this green type of color right there, what is that? Oops, I keep grabbing that picture by mistake. Just want to scroll. There we go. The green are the nonmetals. All right, so I have a sense of the difference, right? A metal is shiny. It's a solid. It conducts electricity usually. It's got some luster. It's malleable. You can bend it and that kind of thing. Whereas nonmetals, they're probably not going to be so shiny. They're going to be like more powders. They're probably not going to conduct electricity, that kind of stuff. They might come in crystalline form, but probably not like a metal. All right, so these are the nonmetals. Not very many of them. Got this little diagonal line kind of here that the greens start with, and then this upper corner. And again, you could throw hydrogen over there if you want, right up there. Those are the nonmetals. So what are these purple ones right here on this diagonal line? Well, they separate the division from the metals and the nonmetals, and accordingly, they do have properties of both. They're called metalloids. I've seen some texts call them semi-metals, like half metals. Metalloids are probably a little more common. They kind of have properties of both a metal and a nonmetal. Now, they might not conduct electricity so great. They might not be quite like a luster like a metal. They have nonmetal properties as well. Boron, silicon, germanium, arsenic. These guys right along this diagonal line. I usually think of a diagonal line started right here, right underneath boron B, and just kind of zigzag it down, zigzag, zigzag over, and you pretty much go along that line that these guys hug. Okay. Aluminum's kind of interesting. It's sitting right next to these metalloids. And in some ways, aluminum does act more like a metalloid or even a nonmetal in certain compounds. So it's right on that dividing line. So do understand and be able to classify, or at least look it up on a periodic table, what's a metal, what's a nonmetal, and what is a metalloid. Okay? And understand that the periodic table is arranged then by chemical properties.